A modern web application is an ecosystem of thousands of interlocking components. As it scales, a single styling error can fracture the entire user interface. This fragility stems from a central paradox in CSS. Its declarative syntax makes it easy to write, but its lack of native encapsulation makes it difficult to manage in large-scale engineering. The root of this difficulty is the global namespace. In traditional CSS, every class shares the same environment. A style defined for one specific element is constantly at risk of colliding with another. Observe this wireframe collision. Modifying a generic button class to red inadvertently changes every button across the application. To fix these regressions, developers write increasingly specific, nested selectors. This creates a bloated specificity graph, a tangled web of dependencies difficult to maintain. Overcoming this structural flaw requires a shift in engineering philosophy. Royal Research suggests that scalable web architecture requires moving away from implicit global cascading toward explicit modular isolation. Achieving this isolation relies on three distinct methodologies: convention-based naming, category-based sorting, and programmatic encapsulation. Mastering CSS architecture is not about memorizing new properties. It is about engineering strict boundaries in a system designed to have none. The first line of defense against global scope bleed is a convention known as BEM, Block Element Modifier. BEM works within the existing cascade rules to prevent conflicts. It uses a strict naming convention to ensure that each selector targets only one specific component, effectively simulating local scope. The first layer is the block, a standalone entity isolated from its environment. Next, the element layer binds a subcomponent directly to its parent block, scoping styles strictly. Finally, the modifier layer uses a double dash flag to alter appearance without writing entirely new classes. By utilizing the single class selector approach, BEM keeps the CSS specificity graph flat. Because every selector has the same weight, the styles are predictable. This flat structure prevents the most common source of regressions: CSS rules unintentionally overriding one another because of their order in the document. Because a BEM block carries all its dependencies within its own namespace, an engineer can move that block to any part of the application without breaking its internal styles or affecting adjacent elements. The success of BEM relies on human discipline. If developers strictly follow the syntax, the CSS remains scalable and styling conflicts are minimized. BEM solves naming at the component level, but massive codebases also require organization at the file level. This is where SMACSS is applied. SMACSS, or Scalable and Modular Architecture for CSS, functions as a framework for categorizing style sheets based on their role in the application. To prevent structural rot, SMACSS separates styling code into 5 categories. Universal resets drop into base, while grid systems go to layout. The module layer holds reusable components. Finally, temporary UI changes and global color modes are isolated in state and theme folders. These methodologies often work together. Royal Research strategies emphasize combining the file categorization of SMACSS with the flat naming of BEM to maximize maintainability. By separating layout from component aesthetics, SMACSS allows teams to work simultaneously without creating merge conflicts in a single style sheet. A third approach shifts the responsibility from developer discipline to programmatic enforcement. Modern layout engines like CSS Grid and Flexbox simplify this by handling complex alignment and spacing through standardized properties. This reduces the need for the deeply nested manual positioning classes that often cause collisions in older architectures. CSS in JS takes this further. Libraries like styled components move styles out of the global style sheet and directly into the JavaScript component layer. Looking at this JavaScript compilation, CSS in JS handles the namespace by generating unique class hashes at runtime, ensuring styles never collide. This also enables dynamic styling. By evaluating logic directly, components react instantly to state changes, eliminating manual class toggles. When paired with CSS variables, this approach provides a centralized mechanism for managing global themes across isolated components. Storing values like a brand color in the root directory creates a single source of truth. That one variable propagates through thousands of isolated components simultaneously. Together, CSS in JS and custom variables represent a shift toward modular architecture that protects engineers from the unpredictable side effects of the traditional cascade. We have examined 3 strategies for scale: BEM's naming conventions, SMACSS file routing, and the programmatic scoping of CSS in JS. While the tools and syntax vary, the underlying objective of these royal research strategies is identical. Each methodology aims to decouple the visual layer from the document hierarchy, establishing clear local scope. The choice of methodology depends on the specific needs of a project, but failing to implement a structure leads to unmaintainable code. The core requirement is to prioritize explicit boundaries over implicit rules. By engineering components that operate independently, developers build applications that scale reliably, turning the unpredictable cascade into a structured, predictable system.